So far in our look at elimination reactions, we've seen many examples where the elimination occurs and the most stable product is produced. These would be the eliminations that follow so-called Zaitsev's rule, and we produce the more substituted alkene in abundance. But we've also seen a few examples under very specific conditions with very specific substrates where elimination occurs and the less thermodynamically stable product is produced as the major product. And this brings up the notion of what's controlling the outcome of a reaction with regard to what the major product is. And we find that often reactions produce the thermodynamic product, but in some rare cases they produce a so-called kinetic product. The thermodynamic product is said to be the product that is the most stable, whereas a kinetic product is the one that is produced most rapidly. They can be, in fact, one and the same, but they are often different products. And so it's important to recognize what's driving a particular reaction. So the most common scenario that we observe is what we see here on the left, where we have a reaction that can produce two possible products, product X and product Y, and from a given starting material. And there's an energy difference between the two products, where for some reason product Y is more stable than product X. So if we think about elimination reactions, this might be a more substituted alkene, this might be a less substituted alkene, and there are isomers. The most typical scenario, and the reason that Zaitsev's rule applies to so many of these types of elimination reactions, is that the activation energy to the formation of the more stable product is lower than the activation energy to the formation of the less stable product. And we're producing the more stable product not because it's more stable, but because it's produced more rapidly and it's going through a more stable transition state. Remember, in an E2 reaction, for instance, there's only a single transition state and then the product is produced. But there are scenarios, think of the examples where we saw Hofmann elimination predominate. And in those scenarios, we actually produced as our major product the less stable product. And the reason that less stable product formed as the major product is that the transition state to its formation was more stable than the transition state that produced the more stable product. And I encourage you to go back and review the Hofmann elimination of the trimethylammonium ion substituted alkane. And in that case, we do in fact produce the less stable product as the major product. And we looked very closely at the conformations of the transition states, and we can see clearly that the more stable transition state leads to the less stable product in those scenarios. So in this discussion, it's important to think about the nature of transition states. And one thing that can help us picture transition states is the so-called Hammond Postulate, named after the physical chemist who gave it to us. And the Hammond Postulate can be stated in various ways, but primarily you see it this way, and that is for an endothermic reaction, the transition state resembles the product. For an exothermic reaction, the transition state resembles the reactant. And what that tells us is something about where the transition state lies along a reaction coordinate. So if we think of an endothermic reaction, such as the example shown here on the left, and we're working our way up to a higher energy product from a lower energy, then the question is where along the reaction progress diagram is the transition state. So if we think about our timeline and we kind of mark starting material and we mark product, you'll notice that the transition state doesn't lie in the middle. It lies closer to the product. And what Hammond tells us from his work is that means that the transition state, whatever the structure of that transition state, it more closely resembles the product than it does the starting materials. And so as we're trying to hypothesize what that transition state is, we would like it to have a structure that is more similar to the structure of the product than we do to the structure of the starting material. Conversely, you can kind of think about the way most reactions happen, where you have a starting material going to a product. We just happen that the reaction progress is shown the other way here. And you can see that in this case, that's an exothermic reaction going in this direction. And that exothermic reaction, by that same logic, has a transition state that lies closer along the timeline to the starting material than it does to the products. And so that transition state should more closely resemble the starting material than it does the product. So it's just a way of kind of thinking about what should that structure be, and thinking about this in terms of a timeline and the change in the structure of the starting material as it transforms into the product. So the punchline is just that an exothermic reaction has a transition state that resembles the reactant, and endothermic reaction is a transition state that resembles the product. And finally, products formed most quickly will look more like the transition state than products that are more thermodynamically stable, assuming that the two products are different. All right, changing subjects to another aspect of elimination reactions and some other reactions that we have already visited. One of the things we find when carbocations are involved in a reaction is that we often see unusual products. So here we have three of the types of reactions that we've talked about so far that all involve carbocation intermediates. The first reaction here is an elimination. More specifically, this is an E1 elimination occurring under acidic conditions where the hydroxyl group is protonated. Loss of water leads to a carbocation. The second example is an electrophilic addition. We looked at these in an earlier chapter where we're doing a hydrohalogenation of an alkene, and you recall that protonation of the alkene leads to a carbocation intermediate. And then finally, this last example is an Sn1 substitution. Now, what's curious about all of these particular reactions, these are all found in the literature, is how the carbon backbone has changed. So focus on this top reaction. You'll notice we have a 4-carbon chain, 2 methyl groups attached to this carbon here. And if we look at the products, we can see that these first 2 products have a carbon backbone that has changed considerably. We do have 4 carbon chains, but we don't have 2 methyl groups on 1 carbon. Seemingly, one of the methyl groups has migrated to a different position. Only this last product retains the same carbon backbone as the starting material. Likewise, in the electrophilic addition, you can see that this second product, you'll notice that we have now a methyl group that has seemingly migrated to where the chlorine was to begin with. And then this last example, you can see that we have the hydroxyl group here and these methyl groups on this position, and at least one of those methyl groups has seemingly migrated over here to the end of the molecule, and now we have a 4-carbon chain as our longest chain in the molecule. So what in the world is going on? The answer is something that turns out to be quite common. These are carbocation rearrangements. So just to refresh your memory, carbocations are positively charged alkyl chains. So there's a carbon somewhere in the molecule that bears a positive charge. They are typically formed when a leaving group leaves and you're left with a carbocation, or they're formed upon protonation of a double or a triple bond. They are reactive intermediates, so they are inherently unstable to normal reaction conditions, although they do have a finite lifetime. we find that the order of stability is such that secondary and tertiary carbocations are really the only viable carbocations that we would find as intermediates in ordinary reactions. Primary carbocations essentially don't exist. The ability to delocalize charge can stabilize carbocations to an even greater extent. And then finally, as a consequence of differences in stability, we're going to find that carbocations rearrange. And they rearrange by what are known as hydride or alkyl shifts. And we're going to look at some mechanisms of how that occurs. So this is the simplest example of a carbocation rearrangement. Thermodynamically, these rearrangements happen to form more stable carbocations from less stable carbocations. And in this example, you can see here on the left that this positively charged carbon is a secondary carbocation. And essentially what happens here is a hydride can hop. Mechanistically, we need one curved arrow saying that that hydrogen with the pair of electrons moves over to where the positive charge was. And that leaves now the positive charge on this carbon, and it's become a tertiary carbocation. And so there's a thermodynamic driving force for the shift, and as we're going to see in a minute, there's a very easy way for this to happen in terms of molecular orbital overlap. It turns out that alkyl shifts can happen in a very similar way. So this hydride could, in fact, be something like a methyl group, and the methyl group can essentially hop over in the same way. So it's a mechanistically analogous rearrangement. All right, so let's take these two of those examples that I showed you and kind of break these down and think about what's going on in these reactions. And we start with the first example, taking that alcohol and placing it into sulfuric acid is going to protonate that hydroxyl group, which produces this oxonium ion. The oxonium ion can undergo loss of water to produce a carbocation. And so we would have this initially formed carbocation. One possibility is that that carbocation gets deprotonated at this terminal position over here by some basic species in the reaction mixture. We've produced water in the previous step, so it could in fact be water, it could be a hydrogen sulfate ion. I'm going to use a water molecule to illustrate this mechanism. And that produces the unrearranged product. But the other thing that can happen is that the hydride, or that an alkyl, a methyl group can shift over. And if a methyl group shifts over, that secondary carbocation, so this is a secondary carbocation, rearranges to form a tertiary carbocation. And that tertiary carbocation can undergo deprotonation in two different ways. One to produce this most substituted product, and the other produce the other alkene that we see here. And we need some base in the reaction mixture. Water is sufficiently basic to deprotonate a carbocation. And we either deprotonate at this methyl group or we deprotonate at that methine group. And so one of the reactions would occur this way, the other reaction would occur that way, and we produce the two products. And so the key transformation in all of this is the rearrangement of the carbocation from a secondary to a tertiary. And those rearrangements are very, very fast. And so we would typically find that The major products would be those of the rearrangement, and the minor product would be the unrearranged. All right, let's think about this second example and what's going on here. And in this example, a similar transformation is occurring. So this is an electrophilic addition of HCl. Markovnikov's rule is in place, so we're going to protonate at the terminal carbon, and we would produce this same secondary carbocation that we saw above. We can get a methyl shift, rearranging this from the secondary carbocation to this tertiary carbocation. And the two different products are formed by the reaction with chloride ion. So if the chloride ion adds to the carbocation, you would form the first product, and if the chloride ion adds to the tertiary carbocation, we produce the second product. So why do these rearrangements happen so rapidly? And the answer is there's a very strong thermodynamic driving force going from the less substituted carbocation to a more substituted. So in this example, we have a secondary carbocation. This is the carbocations we drew on the previous slide, by the way. And here is the tertiary carbocation that forms. Mechanistically, it's just this pair of electrons holding that methyl group migrating over to the positively charged carbon. And so the electrons that are moving is this pair of electrons here, and it becomes that pair of electrons. And this can all happen because of very efficient orbital overlap. The sigma bond is essentially migrating, and when it migrates, it's simply overlapping with the empty p orbital of the carbocation. If these two can achieve alignment by just simple rotation around the carbon-carbon bond between the two, then we kind of have this transient pi bond where the methyl group is shifting from one side to the other, and it will continue, and there's a strong thermodynamic driving force for this because we're generating the more stable carbocation from the less stable carbocation. So what we've learned is that due to these carbocation rearrangements, you get further reaction on a population of rearranged molecules, and you get this variety of products. Now, it turns out that in most cases, this is something that chemists want to avoid. We don't like having mixtures of products because that entails separations, and separations are often kind of inherently inefficient. And so as such, organic chemists typically prefer the bimolecular reactions, the Sn2 and E2 reactions, because rearrangements are not complications in those, whereas Sn1, E1 conditions often lead to these mixtures of products, and in some cases unexpected products until you kind of examine things after the fact. So that finishes chapter 8. Here you'll find the usual list of recommended study problems. It's quite extensive in this chapter. And we're going to see carbocations, and we're going to employ substitution and elimination reactions extensively throughout the rest of the semester and out the rest of the year.